Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from Department of Physics, Central University of Haryana. Today we are going to discuss about a module commuting operators under the paper Quantum Mechanics 1. So students, let us see what all we're going to learn in this module. Firstly, we'll know the important role played by the two commutating operators in determining the basis vectors in the Hilbert space of a physical system. We'll learn the necessary and sufficient condition so that the operators possess a complete orthonormal set of common eigenvectors. Then we learn through an illustrative example the meaning of the term degeneracy of eigenvalues and how it is lifted. After that, we'll know what constitutes a complete set of commutating operators and how these are obtained. And finally, we learn through an example how a complete set of commuting operators is obtained. So now, as you know, in the previous modules, we studied about the dynamical variables which could be simultaneously assigned definite values in a given state and are represented by commuting Hermitian operators. In contrast, we also have variables which cannot be assigned specific values and are represented by non-commuting operators. Energy and momentum of a free particle can be the example of commuting operators, whereas the x-coordinate and the x-component of the momentum are examples of the non-commuting operators. So, in the first part of this module, we shall discuss the necessary and sufficient condition so that the operators possess a complete orthonormal set of common eigenvalues. We shall also introduce a complete set of mutually commuting operators such that they have one and only one eigenbasis. To make these concepts clear, a couple of illustrative examples are also going to be discussed. Commuting operators. As we have discussed in detail about the energy and the momentum operators previously, we see that the energy and momentum operators of a free particle is the well-known example of commuting operators. Let us come on to the basic theorem for commuting operators. So the basic theorem states that the necessary and sufficient condition for the existence of a basis with respect to which the Hermitian operators A and B represent diagonal matrices is that they commute, with commutation relation of operator A with operator B, which is equivalent to operator A times operator B minus operator B times operator A is equal to 0. Now let us suppose that there exists a basis ket vector A, ket vector A prime, ket vector A double prime, and so on, which is a common basis of the eigenvectors A and B. That means that the above defined basis acts as a common basis for both these eigenvectors, so that we can define operator A acting on ket vector A is equal to A times ket vector A, where A is the eigenvalue corresponding to operator A, and operator B acting on ket vector A is equal to B times ket vector A, where B is the eigenvalue of the operator B. Now, operating the first from the left by operator B and the second by operator A, we see that operator B acting on operator A acting on ket vector A is equal to A times operator B acting on ket vector A is equal to AB times ket vector A, where A and B are the eigenvalues corresponding to operators A and B respectively. And similarly, operator A acting on within brackets operator B acting on ket vector A is equal to B times operator A acting on ket vector A is equal to BA times ket vector A, where B and A correspond to the eigenvalues of the operator B and operator A respectively. Commuting operators. From the two equations that we have discussed above, we can get operator A, operator B minus operator B, operator A within brackets acting on ket vector A is equal to 0. Now, since we get this result from the above two equations, and since this result is true for all ket vectors A, we have operator A, operator B minus operator B, operator A is equal to 0 in order to have a non-trivial solution. This condition or this equation that we have written is actually a necessary condition for the two operators to commute, and its converse is also true. So let us suppose that operator A, operator B minus operator B, operator A is equal to 0, and then let us choose the basis where the basis vectors are the eigenvectors of the operator A, such that operator A acting on ket vector A is equal to A times ket vector A, where A is the eigenvalue corresponding to operator A acting on the ket vector A. Then operator A, operator B acting on ket vector A is equal to operator B, operator A acting on ket vector A is equal to operator B times A times ket vector A is equal to A times operator B acting on ket vector A, where A is the eigenvalue corresponding to operator A acting on ket vector A. Accordingly, we have operator B acting on ket vector A is also an eigenvector of operator A with the same eigenvalue A. Now, if A, that is the eigenvalue A, is non-degenerate, then there is only one eigenvector, ket vector A, corresponding to the eigenvalue A. In that case, operator B acting on ket vector A should be linearly dependent on the ket vector A, or can be expressed as a linear combination of the ket vector A. Commutating operators. So we are discussing the case where the eigenvalue A is non-degenerate. Then in such a case, there is only one eigenvector corresponding to the eigenvalue A, and in that case, any other operator B acting on A should be linearly dependent on A. What that means is that we can write the dependence in the form of the following equation: C1 times operator B acting on ket vector A plus C2 times ket vector A is equal to 0 for C1 not equal to 0 and C2 not equal to 0. So what we have done is basically we have written the operator B as a linear expansion in terms of the ket vector A. Now rearranging the terms in the above equation in the expansion, that is the linear expansion, we can rewrite the above equation as operator B acting on ket vector A is equal to minus C2 by C1 times ket vector A, and this is equal to eigenvalue B times ket vector A. So from this equation one can see that operator B acting on ket vector A gives us an eigenvalue B, where the eigenvalue B are simply the coefficients of the linear expansion. That is, the eigenvalue B can be written as minus C2 by C1, where C1 and C2 are the coefficients of the linear expansion. Now, if the eigenvalue A is G-fold degenerate, it means that there are G linearly independent vectors ket vector AK, K going from 1 to G, such that operator A acting on ket vector AK is equal to A times ket vector AK, where A is the eigenvalue corresponding to each of the linearly independent AK ket vectors. Let us assume that these are orthogonal, that is, bra vector AK ket vector AJ is equal to delta JK, delta KJ. Also, consider for the sake of simplicity the case when G is equal to 2, that is, there is two-fold degeneracy. So let us define our vector A as ket vector A is equal to alpha times ket vector A1 plus beta times ket vector A2, where alpha and beta are scalars. Now, since operator A is linear, therefore we can write operator A acting on ket vector A is equal to alpha times operator A acting on ket vector A1 plus beta times operator A acting on ket vector A2, and this is equal to A times ket vector A. That is, we have that the ket vector A is the eigenvector of the operator A, which is having the eigenvalue A. Now, what we have to show over here is that there are non-zero scalars alpha and beta as given in the above equation, such that operator A acting on ket vector A is equal to A times ket vector A, and operator B acting on ket vector A is equal to B times ket vector A. So we can write operator B acting on ket vector A is equal to operator B acting on alpha times ket vector A plus beta times ket vector A2. So what we have done over here is we have used the above definition of our ket vector A in terms of the expansion involving alpha and beta, and we have defined our operator B acting on ket vector A as operator B times acting on alpha times ket vector A1 plus beta times ket vector A2, and this is equal to B times alpha ket vector A1 plus beta times ket vector A2. Degenerate case. Now, using the above equations and taking the scalar product successively with ket vector A1 and ket vector A2, we get operator B acting on operator A acting on ket vector A is equal to A times operator B acting on ket vector A is equal to AB times ket vector A, and operator A acting on operator B acting on ket vector A is equal to B times operator A acting on ket vector A is equal to B times A times ket vector A, where Bjk is equal to bra vector Aj operator B ket vector 8k. Now, the condition for the existence of non-trivial solution, that is, solutions for which alpha and beta are not equal to 0, is that the determinant of the matrix representing the coefficients be 0, that is, the matrix with elements B11 minus B, B12, B21 and B22 minus B is equal to 0. Solving this determinant, we get the equation B square minus B within brackets B11 plus B22 times B plus within brackets B11 times B22 minus modulus square B12 is equal to 0. Now, as you can see, this is a quadratic equation in B, and so solving for B, we get two roots for this quadratic equation, which are given by B1 is equal to B11 plus B22 upon 2 plus half bracket open within brackets B11 plus B22 whole square minus 4 times within brackets B11 B22 minus modulus square B12 whole bracket closed to the power half, and the other root is given as B2 is equal to B11 plus B22 upon 2 minus half bracket open within brackets B11 plus B22 whole square minus 4 times within brackets B11 B22 minus mod whole square B12 bracket closed whole to the power half. Now here the two roots are equal. Conditions for removing degeneracy. Now, if we look at the two roots of the quadratic equation as written above, then we see that the two roots are equal if bracket open b11 plus b22 bracket closed whole square minus 4 times within brackets b11 b22 minus mod whole square b12 is equal to 0. That is, if within brackets b11 minus b22 whole square plus 4 times b12 mod whole square is equal to 0. Now, the two roots will be equal only if b11 is equal to b22 and b12 is equal to b21 is equal to 0. In this case, b1 is equal to b2 is equal to b is equal to b11 is equal to b22. It thus follows from the above discussion that operator b acting on ket vector a1 is equal to b times ket vector a1 and operator b acting on ket vector a2 is equal to b times ket vector a2, where b is the eigenvalue corresponding to the operator b. Now showing that operator a1 and now showing that ket vector a1 and ket vector a2 are degenerate eigenvectors of the operator b also. So what will happen when b1 is not equal to b2? In that case, one or both of the following conditions are satisfied. The first condition is b11 is not equal to b22, and second condition is b12 is not equal to 0. Now, if only condition 1 is satisfied, then we will get b1 is equal to b11 and b2 is equal to b22. Conditions for removing degeneracy. Now, corresponding to these values of b, that is, b1 is equal to b11 and b2 is equal to b22, we get two sets of values for alpha and beta. Denoting these values of alpha and beta by alpha 1 and beta 1, we have the possibilities alpha 1 is equal to 1, beta 1 is equal to 0, alpha 2 is equal to 0, beta 2 is equal to 1. So that we can write ket vector A1 is equal to alpha 1 ket vector A1 plus beta 1 ket vector A2 is equal to ket vector A1. Ket vector A2 is equal to ket vector A2. Thus, operator B acting on ket vector A1 is equal to B1 times ket vector A1, and operator B acting on ket vector A2 is equal to B2 times ket vector A2. This means that the eigenvectors of the operator B belong to different eigenvalues. When B12 is not equal to 0, then we can use the linear combinations given by ket vector A1 is equal to alpha 1 times ket vector A1 plus beta 1 times ket vector A2, and ket vector A2 is equal to alpha 2 times ket vector A1 plus beta 2 times ket vector A2. Summarizing different cases. Now, with alpha I not equal to 0 and beta I not equal to 0, as we have seen previously, we get operator B acting on ket vector AK is equal to BK times ket vector AK with K equal to 1, 2. When operator A has degenerate eigenvalues, then we see that there are the following possibilities, and these possibilities are: A. Every eigenvector of operator A is also an eigenvector of operator B. So here we have further 2 points. One, the degenerate eigenvectors of operator A are degenerate eigenvectors of operator B also. And the second point is that the degenerate eigenvectors of operator A belong to different eigenvalues of operator B. So in this case, the degeneracy is said to be removed by the Hermitian operator of operator B. And the other possibility is when every degenerate eigenvector of operator A is not an eigenvector of operator B, but there are linear combinations of the degenerate eigenvectors which are degenerate eigenvectors of both operator A but are non-degenerate eigenvectors of operator B. The degeneracy is removed in this case by operator B. Complete set of commuting operators. Now let us suppose we have a basis of linear vector space formed by a complete set of eigenvectors, ket vector an, of a Hermitian operator A. The reason why we are taking Hermitian operator is because in case of Hermitian operators, operator A is equal to operator A dagger, or the operator A is equal to its adjoint, and thus the eigenvalues corresponding to Hermitian operators are all real. So, if the operator A has degenerate eigenvalues, that is, that the eigenvectors are not uniquely specified by the eigenvalues of the operator A, there being more than one eigenvectors corresponding to the eigenvalue an. So, we then choose another operator B which commutes with the operator A and construct an orthonormal set of vectors which are simultaneously the eigenvectors of operator A as well as of operator B. And then, if this basis is unique in the sense that to each pair of the eigenvalues an, bm, there corresponds one and only one eigenvector, the operators A and B are then said to form a complete set of commuting operators. The degeneracy is then said to be completely removed. However, if we see that even after considering another operator B, we are still not able to completely remove the degeneracy, which means that for each eigenvalue an or bm, there correspond more than one eigenvectors, then we keep on choosing more and more such operators and then try and find out a set of eigenvalues such that these eigenvalues correspond to one and only one eigenvector, and the complete set of such operators for which the degeneracy is completely removed then forms the complete basis set of commuting operators. Complete set of commuting operators. In case the degeneracy is not removed, we can go on adding operators until we have a set operator A, operator B, operator C, and so on till operator L of mutually commuting operators such that they have one and only one common basis. In this case, we would have a common eigenstate uniquely specified by the eigenvalues an, bm, cl, and so on till lq, and the corresponding eigenvalue equations can be written as operator A acting on the common basis ket vector an, bm, cl, and so on till lq is equal to an times the common basis ket vector an, bm, cl, and so on till lq. Similarly, operator B acting on the common basis ket vector an, bm, cl, and so on till lq is equal to bm times common basis ket vector an, bm, cl, and so on till lq. And in this manner we can continue. And finally, operator L acting on the common basis ket vector an, bm, cl, and so on till lq is equal to lq times common basis ket vector an, bm, cl, and so on till lq. Here an, bm, cl, and so on till lq are the uniquely defined eigenvalues corresponding to the eigenvectors of the common basis and the operators operator A, operator B, operator C, and so on till operator L respectively. Thus, the operators A, B, C, and so on and L are then said to form a complete set of commuting operators. So students, now let us summarize what all we have understood in this module. Firstly, we understood the important role played by the two commuting operators in determining the basis vectors in the Hilbert space of a physical system. Then we learnt the necessary and sufficient condition for commuting operators to possess a complete orthonormal set of common eigenvectors, where orthonormal set means that the operators, when acting on the same state, give a value of 1, that is, a bra and a ket vector of the same state return a value of 1, and if they are of different states, then the result is 0. Further, we learnt through an illustrative example the meaning of the term degeneracy of eigenvalues. That means that for a single eigenvalue, there corresponds more than one eigenvectors. And also we learnt how this degeneracy of the eigenvalues can be lifted. Then we learnt how we came to know what constitutes a complete set of commuting operators and how these are obtained. So we learned what do we mean by a complete set, and then using the property of completeness and closeness, we then were able to obtain the complete set of commuting operators. And finally, we learned through an example how a complete set of commuting operators is obtained. Thank you.